Alrighty, part 2. So, in the previous video we looked at converting between mixed and entire radicals. Now we're going to look at comparing and ordering them, and in the previous video as well we looked at identifying restrictions. So let's get to where we left off. So, ordering these, in order to order the fractions in ascending order, it is useful to turn them all into entire radicals, because we do know that root 5 is bigger than root 3, but is 4 times root 5 bigger than 5 times root 3? It can be a little difficult to actually figure that out. The cleanest way of doing it is, what if we put them all under a square root, and then they're comparable? Let me show you. So if we take this 5 and root 3, if we were to convert that into an entire radical, remember we got to put this 5 underneath a square root. In order to do that, we are going to square root 5 squared. These two values are the same. The square root of 5 squared is 25, the square root of that is 5. So they have the same value, but now we have the advantage of it being under a square root and combinable with this root 3. So let's put them together under one big root. 5 squared is 25, and 3 square root 3, just like that. And now we can finish solving that, and 5 root 3 is the same as root 75. Now if we do the same thing with a 4 root 5, we would actually be able to compare the two square roots. So let's do that. Let's 4 root 5. Let's put the 4 underneath the square root by squaring it. And then we've got our root 5. This is 16. We'll put it under one big root. 16 times 5. And 16 times 5 is 80. So 5 root 3 is a smidge smaller than 4 root 5 is. They're comparable now. They're a lot easier to determine which one's bigger and which one's smaller now that they're both entire radicals. Let's have a look at the other two and we can compare them all. Root 51 is already in its form, so that's nice. It's already as an entire radical, so we just need to deal with the 2 root 10. So 2 root 10, let's put the 2 under a root by squaring it. So root 2 is 2 squared times root 10. Put it under one big root. 2 squared is 4 times 10. And that ends up being root 40. So if I were to order these 5 radicals, it's a lot easier to see which one's biggest and which one's smallest now. The smallest one is 2 root 10. The next smallest one is root 51. The next smallest one is root 75. And then our largest radical is root 80. Sorry. I'm going to change that in its original form. The next biggest one was 5 root 3. And 4 root 5 is our biggest. So adding and subtracting radicals. I mentioned in the previous video that it is useful to imagine these as x's to kind of connect together your previous skills. We do know that let's imagine this was 5x plus 3x, where x is equal to, if x were equal to root 2, we could convert these all into simple variables, and then it's a lot easier to see how they're going to combine. 5x plus 3x is 8x, minus 2x is equal to 6x. Now, we know that x is equal to root 2, so our final answer here is going to be 6 root 2. Now we don't want to actually always convert to x's. That's a little bit of extra work. Let's just imagine them as x's and just add or subtract the coefficients. So if I had 5 root 2 plus 3 root 2 minus 2 root 2, think of it like this. I have 5 root 2's and 3 root 2's. If I were to combine those, I would have 8 root 2's. And then take away 2 of those root 2's, and now I'm at 6 root 2's. So when you're adding and subtracting, values with the same radical, values with the same radical can be combined through addition and subtraction. If they have a different radical, they can't be combined. So let's have a look over here at this one. We've got a third root 7 and a square root 7. The square roots and third roots, you can't combine them. But you can combine third roots with other third roots if they have the same radicand. Same thing as here. We can combine our square roots with other square roots, again, assuming they have the same radicand. So, if you want to think of it a different way, let's go with our variable strategy again. The third root of 7 is going to be a different number than the square root of 7. So if we were to define them as variables, we'd have to define them as different variables. The third root 7 we could define as x, but the square root of 7 being a totally different number than the third root of 7, oopsie, the square root of 7 being a totally different number than the third root of 7, third root and square root are different numbers, we would have to assign a different variable. So let's pretend we're doing the variable thing, and then we'll scratch that just for linking purposes. Let's change this into 3. We said third root of 7 is x, so 3x minus, we said the root 7's are going to be y, plus y, plus 4x. Now it's probably a little bit easier, if you can connect these together, to see how we would solve these out. The 3x and 4x would be 7x, and the negative 6y plus y would be minus 5y. So our answer with the radicals is going to come out something like that. Like I said, we don't want to actually convert to variables. That's extra work. Let's just work with the radicals. But hopefully this gives you a good visual on the process, on how to approach it. So with 3 cube root 7's and 6 square root 7's plus 1 square root 7 plus 4 cube root 7's. So we can combine together the 3 cube root 7's and the 4 cube root 7's, and we would have 7 cube root 7's. And then we combine together the negative 6 square root 7's with the 1 square root 7, and that would be our minus 5 root 7. And there's nothing we can do with these separate roots. So we have to leave it as that. So what if we had entire radicals like this? The goal here would be to try and get as many similar radicals as we can. And the way to do, a good way of doing that is to turn them into mixed radicals and see which ones are combinable and which ones are not. So let's do some more factor trees. We'll eventually let that go once we get a little bit better at these. So 18 can be split into 9 and 2, and then 3 and 3. 27 can be split into 9 and 3, and then 3 and 3. And then 8 can be split into 4 and 2, and 2 and 2. So let's rewrite all of our radicals to try and spot out our perfect squares. We got 2 times 2 times 3 is 12, plus 3 times 3 times 2 is 18. 3 times 3 times 3 is 27. And then 2 times 2 times 2 is 8. So we have some perfect squares in here. Here is a pair. Here is a pair for this. Here is a pair for this. Here is a pair for this. So we can pull at least some square root out of each of these radicals. So the 2 times 2, that is the perfect square of 4. So the square root of, so that can be pulled out. The square root of 4 is 2. So that comes out, and the only thing left in the radical is 3. In this one, the 3 times 3 is a perfect square. We can pull that out as a 3. The only thing left under the radical is a 2. Minus, again, 3 times 3 comes out. It's a perfect square. And 2 times 2 is a perfect square. The square root of 4 is 2. Now we can have a look and see if any of them have the same radical. If they have the same radical, you can add or subtract the coefficients. So this root 3 and this root 3 have the same radical, and this root 2 and root 2 have the same radical. So let's combine the root 3's. So 2 root 3's, take away 3 root 3's, and we're left with negative root 3. So minus 1 root 3. And then if I had 3 root 2's and 2 root 2's, I would have 5 root 2's. And that's as far as we can go with those, without actually trying to throw it into a calculator. So over here, some of them are mixed, some of them are not mixed. Let's break them fully down and see if there's anything that's combinable. 4 root 3, there's nothing further we can simplify from 3. It's already a prime number. There's no common factors that can possibly be pulled out, so that one is going to stay as is. If there's no common factors, there's no pairs that you're going to be able to pull out. Now I'm going to jump away from the factor trees for these. Square root 20, feel free to use the factor trees if they help you. If this helps you define and figure out which ones are pairs and which one are not, that's all good. A factor of 20, that's a perfect square, is 4. If we pull 20 apart into 4 and 5, then we have a perfect square that we can pull out. Let's keep going. A perfect square factor of 12 is again 4. So 4 times 3 would give us 12. And a perfect square factor of 45 would be 9. 9 times 5. So let's bring out those perfect square factors that we just isolated. And we'll have 4 root 3 plus, it's going to be 3 times 2, because we're turning this root 4 part. We're square rooting 4, and it comes out as a coefficient of 2. You're going to have to multiply those two together. It comes out as a multiple for the coefficient. And then what's left under the radical is 5. Do the perfect square of the 4, and we're left with a root 3. Do the perfect square of the 9, and that's a 3 root 5. Okay, let's combine some of these together. We've got a root 3 and a root 3. So 4 root 3's minus 2 root 3's. We're left with 2 root 3's. And then this is 6 root 5s and 18 root 5s. So 6 plus 18 is 24 root 5s. We cannot combine root 3s and root 5s, so that's as far as we can go. Alright, so let's throw in some geometry, working with perimeter. So we know that perimeter is, for a rectangle, is found by doing the length times width length plus width length plus width plus length plus width, or 2L plus 2W. So let's do that. So our perimeter for this would be done by taking, let's do perimeter equals 2L plus 2W. You could equivalently do L plus L plus W plus W. You're going to get to the same result. This one's just probably going to get you there in less steps. So 2 times the length will be 2 times 4 root 2 minus root 3. And we're going to add that with 2 widths, which is 2 root 3. So 2 times root 3. So distribute the 2 inwards. Again, imagine these as x's. What would be 2 times 4x? It'd be 8x. The setup is the same. So 2 times 4 root 2 is 8 root 2's. 2 times root 3 is 2 root 3's. And then 2 times 2 root 3's would be, so again, imagine 2 times 2x would be 4 root 3's. See what we can combine here. Root 2's don't combine with root 3's, but root 3's certainly combine with other root 3's. So the 8 root 2 is as far down as we can go for that one. But minus 2 root 3's and plus 4 root 3's, we would have positive 2 root 3's. And that is our perimeter. So like I said, you could add them all separately. You could do, so if our length was 4 root 2 minus root 3, then we could write all that out. 4 root 2 minus root 3 plus 4 root 2 minus root 3. If our width was 2 root 3, then plus 2 root 3 plus 2 root 3. And then we can combine them all together. So 4 root 2's, 4 root 2's, that's 8 root 2's. Minus 1, minus 2, root 3's, plus 2, we're at 0, plus 2 at the end is 2 root 3's. They get you to the same answer. And of course, it's the same equation. Last one to get. So if we define this side as, or find the perimeter of the following rectangle, answer it in simplest form. So let's define our 2 sides, our lengths and our widths. So we'll call that length and we'll call this width, just to switch it up. And our equation is perimeter is equal to 2 length plus 2 width. Substitute in our lengths and our widths. And we get 2 times root 27 plus 2 times 2 root 3. So if we were to do that, we would have 2 root 27 plus 4 root 3. Again, imagine this as a variable. 2 times 2x would be 4x. So 2 times 2 root 3 would be 4 root 3. Now, this 27, that's not a prime number, so it has some factors. If we were to pull the 27 apart into its prime factors, 27 can be split into 3 times 3 times 3. You can do a factor tree just to test that out, but 2 times root 3 times 3 times 3. This 3 times 3 pair here is a perfect square. So we're going to pull that out of the perfect square in a moment here. So the square root of 3 times 3 is 3. So 2 times 3, and then all that's left under the radical is root 3. And 2 times 3 is 6. So we have 6 root 3's plus, made a mistake there, that's 4 root 3's. Nothing changed there. And 4 root 3's. If I have 6 of something and 4 of those same things, so 6 root 3's plus 4 root 3's, that's 10. 10 root 3's. And that's our final perimeter. That's all for this one. Thanks for joining.